Hi there, this is Mr. Sutton giving you the first in a series on similarity lessons. In this one, we'll talk about ratios and proportions, specifically how to solve problems involving these two items. And for our real-life application, we'll use proportions to figure out the number of trees in a certain area. For your warm-up on this one, see if you can solve these two problems. All right, let's see how we did. So for this first one, since we have two fractions with an equals between it, we can use the technique of cross-multiplying to get rid of those fractions. So we've got 10 times x is 10x, and then 6 times 16, that'll be 96. Then we just divide by 10, and we have x equals 9.6. Similar idea over here, only this time we have to be careful because there are multiple terms on this side of the fractions. So in this situation, we need to distribute when you have more than one term. So we're going to have 2 times m plus 5, the whole thing in a parentheses, equals 3 parentheses m plus 1. We want to make sure again that we don't forget to distribute, so I always include these parentheses right after cross multiplying. So then we'll have 3m plus 3 and 2m plus 10. Subtracting 2m over here, we've got an m. Subtracting 3 over there, we've got a 7. And that's it for that one. Before we move on to the next page, though, let's just quickly check our answer. So if you plug 7 in for m, over in the first fraction we'll have 3 over 7 plus 5, so 3 over 12. Second fraction, 2 over 7 plus 1, so 2 over 8. And those don't look the same. But wait, you say, these reduce to the same thing, 1 over 4. You're right. We would say that the fractions, the numerator and the denominators, have the same ratios. Let's talk about ratios now. So we're going to use the word ratio quite a bit, and when we use this word, we are talking about a comparison of two numbers using division. Now there's lots of ways to write ratios. You could write it with a colon like this. We would call this 2 to 1. You could literally write the word 2 in there, and this is how odds in sporting events are usually expressed. Or you could use the good old fraction. These all mean the same thing. And not all ratios have to come in twos either. You could have something called an extended ratio, which is just more than two numbers in a ratio. For example, we could say that the sides of some triangle are in a 3 to 2 to 1 ratio. One side is always 3 times as long as another side, and that side is half as long as some other side. So we can have as many numbers as we want in a ratio depending on what we're trying to do. And if we have two separate ratios together in an equation, we call that a proportion. So for example, when we checked our answer on the second warm-up, when we had 3 over 12 equals 2 over 8, this is an example of a proportion. Let's see how we can use ratios to find some unknown triangle measures. Let's say the measures of the angles in a particular triangle are in a 1 to 2 to 3 ratio. What are those measures? So a good thing to start with would be a diagram, because I'm a very visual person. And it'd be nice if we had a way of talking about the angles in here that we're trying to find. So one way you can do this is by using the ratio and putting an x behind each part of that ratio to give you expressions for the angles. We don't know what the angles are, but we know that there's some number I can multiply 1, 2, and 3 by to actually get all the different angles. So we can call our first angle x, and that means our other angles are going to have to be 2x and 3x. Again, we don't know what x is. We don't know what all of these angles are actually getting multiplied by, but we know they are in a 1 to 2 to 3 ratio. Once you've got an expression for the angles, you can use those different ratio parts to make an equation. So what ties all of these angles together? Well, we know in a triangle the angles have to add up to how much? Oh yeah, 180. So we can say 1x plus 2x plus 3x equals 180. And then just go ahead, solve for x, and find the actual measurements. So we've got 6x equals 180. So x is then going to be 30, and 30 happens to be one of our angles, so 30 degrees. And then we can just multiply x by these other ratios to get the other angles here. So we've got 2 times 30, which is 60, and 3 times 30, which is 90. Let's do another ratio problem. Let's say the perimeter of a rectangular room is 48 feet and the ratio of its length to width is 7 to 5. What is the length and the width of that room? Pause the video and see how far you can get on this one on your own. All right, so I'm going to start this off by drawing a picture of a rectangle. We know the perimeter is 48 feet, so we'll say P equals 48. And let's label this diagram now. If our length to width is 7 to 5, that ratio, then let's call this side here the width and this longer side the length. So I'll put a 5x on each of those widths, and then 7x will be each of the lengths. Now what do we know about perimeter? Well, the perimeter of a rectangle is just 2 times the length plus 2 times the width. In other words, add all the sides together. So we've got 2 times 7x plus 2 times 5x. And that's all going to equal 48. So that's 14x and 10x, which is 24x. Dividing by 24, we get x equals 2. But be careful here. We haven't actually answered the question. We need the actual length and width. So for the width, we've got 5 times what we just got for x. That'll be 10. What are our units here? Oh, feet. So 10 feet. And then our length will be 7 times 2 for 14 feet. And you can always double check this. If we add 10, 10, 14, and 14 together, that's 20 plus 28 gives us a perimeter of 48 feet. We're going to shift gears a little bit. Let's say the ratio of 2 side lengths for this triangle is given as follows. AC to AB is a 3 to 4 ratio. The ratio of this side to this side here is 3 to 4. Find the variable x. So this is definitely a different kind of problem, because here we know some things. We know the actual length of one of these sides, and we also know the ratio of the 2 sides to each other. So in this situation where we know the ratio of 2 sides and we know the actual value of one of the sides, we can actually use a proportion to solve for the missing side. So in a proportion, you're saying 2 ratios are the same, so then the ratio of x to 12, which we can write as the fraction x over 12, that has to be the same as 3 over 4. Cross multiplying, we've got 36 and 4x, and dividing we get x equals 9. To wrap this one up, we're going to do a real-life problem. As part of an environmental study, you have to estimate the number of trees in a 150-acre area. That's a lot of tree counting if you're doing that whole area. So instead, you count 200 trees in a 2-acre area, and you notice the trees seem to be evenly distributed. So you didn't just find the area that had the most trees in it. Everywhere has the same density of trees. Based on that, estimate the total number of trees. So pause the video and see if you can set up a proportion in the form part over whole equals part over whole, and then solve it. So what's this whole part over whole business? Well, there's 2 quantities in this problem. We have the number of trees and the number of acres. So one of the parts is that we have 200 trees. That's part of the whole forest, which is the total number of trees. And then we also have this 2 acres, the sample acres, sample size acres, and that's part of the whole acreage. So we have 200 trees over some unknown, which we'll call T, and we have 2 acres over 150 acres. The ratio of one part to whole is going to be the same as the ratio of the other part to whole. Cross multiplying, we've got 2t equals 30,000. So t then is going to be 15,000 trees. Way better than counting all of those. This concludes our lesson on ratios and proportions. Until next time, this is Mr. Sutton signing off.